exercise solution for chemical kinetics, and today we'll be doing problem number 4.16 to 4.20. So let's start 4.16. Here they have given the rate constant for a first order reaction is 60 per second. So the very first information is given as value of rate constant, which is 60 per second. What they are asking you to do, how much time will it take to reduce the initial concentration of reactant to its 1/16th value. Okay, so we have to calculate time taken, and time taken for a particular change. What is the change? Change is initially. So what we suppose that initial concentration is taken as A naught. Okay, so the concentration at a time t is given as A. Okay, and this value in our case is given as A naught by 16. That is, it is 1/16th of the initial amount. Okay, this is given in the question. Now we will use the equation that we use for first order kinetics as given in the question, and this is time can be calculated as 2.303 divided by rate constant log of initial concentration, that is A naught, divided by concentration at a given time, that is A. And in our case, this is 2.303 divided by K log of initial concentration A naught divided by A naught by 16. Okay, so what we have here, we can simplify this. A naught will cancel out, and what we are left with, this is equal to 2.303 divided by, we will put down the value of K, which is 60 per second, and log of 16, because here 16 will come in numerator. So we will find out from the log table value of log 16, and after multiplication final answer will be getting as 4.62 into 10 raised to the power minus 2 second. This is your answer. That is time taken for conversion of original amount to 1/16th of it is this time. This is the value of the time. This is your answer. Now the same problem we can do alternatively in another way. Now question arises why we are trying another method, because sometimes we do not have log table, we do not calculate the values from the log table. Therefore, if we want to avoid such type of calculation, and if we don't want to calculate from this equation, we can do the same in another way. Okay, so what we will be doing here, just have a look. Initially at t is equal to 0. Okay, initially amount of A that we have is A naught. Fine. Now we pass up time, and that time is equal to the t half. So after a gap of time which is equal to half life of this compound, amount which is left is A naught by 2. This is by definition. T half is the time taken when half the amount is amount left is half of the original amount. Okay, so after 1 half life, amount left will be A naught by 2. Now after 2 half lives, then when time is equal to 2 t half, what will be? It will be A naught by 2 and multiplied by 1 by 2. So it will become A naught by 4. Okay. In the same manner, if we continue this, t is equal to n times of t half. Like suppose we take n t half. So in that case, amount left will be A naught divided by 2 raised to the power n. and where m stands for number of half-lives. Now in our case, this value, that is your amount of substance left, amount of substance left, that is, it is given by the formula A naught by 2n, and in our case it is A naught by 16. Fine. So from here, what we can find out here, have a look in the denominator on the left and the right hand side. Your 2n is equal to 16, therefore n is equal to 4. So what we have, T half, how many half-lives are there? There are 4 half-lives when we want 1 upon 16th of the original amount. So now what we will do, we will calculate T half, because we know the value of rate constant, that is 0.693 divided by 60 per second. The value is given. This, when we calculate, we are getting value 0.1155 second. Okay, this is the value of T half. Now amount left will, in this case, time taken will be calculated as time taken for the conversion will be equal to number of your T halves multiplied by value of T half. So in our case, 4 half-lives are there, we calculated here, and the value is 0.1155 second. So the value again after multiplication we are getting as 4.62 into 10 raised to the power minus 2 second. So this is the value of time taken. The same answer we can get from first method as well as from the second method. The only difference is there in the second method, we need not to do the complex calculation and we do not need log table. Okay, now come to the next question, that is 4.17. Here what they are saying, during nuclear explosion, one of the product is strontium 90. Okay, this is the byproduct of nuclear explosion with a half-life of 21.1 year. Okay, so the very first information they have given that for a product of a nuclear explosion, a compound is produced which is radioactive, which is strontium 90, and for this half-life is given as 28.1 years. Okay, in the second part they say if 1 microgram of this was absorbed in the bones of a newly born baby instead of calcium, okay, how much of it will remain after 10 years and 60 years if it is not lost metabolically? So what we have, what next information they have given for the same, that is initial amount is given, that is A naught is given to us, which is 1 microgram of what, strontium 90, and they are asking how much of this will remain after 10 years, the first quantity that we have to calculate, and after 60 years. And now you know it very well that radioactive decay follow the first order kinetics. Yes, so what we can do, first order reaction, because it is radioactive decay. So what we can find out, we can find out decay constant, and this decay constant, which is K, this is equal to 0.693 divided by T half. We know the value of T half, so it will be 0.693 divided by 28.1, which is equal to 2.46 into 10 raised to the power minus 2 per year. Okay, so this is the value of K. This value of K we will be using later on in our calculation. Okay, now first we will calculate amount of strontium 90 left after 10 years. After 10 years. Okay, first we will calculate this quantity. So we will write down the same equation. K, as we write for first order reaction, K is equal to 2.303 divided by time taken for a change where we have log of initial amount divided by amount left at a particular time. Now we will put down the values, okay, and before putting down the values, since we are having the values in the log form, therefore it is easy that first we rearrange the equation. Okay, so what we rearrange, we will keep log values on one side, so we can write it as the same, your K into time taken divided by 2.303 is equal to log A naught divided by A. Now we will put down the values. So 2.46 into 10 raised to the power minus 2 per year into 10 year, because we have to find out for after 10 year what change is there, divided by 2.303 log of log A naught. A naught is the initial amount, it is 1 microgram. So this is equal to log of 1 minus log of A. We will subtract the quantity in the language of log, which is in denominator. Okay. So we will calculate the value, and after calculation we are getting value as 1.068 into 10 raised to the power minus 1 is equal to log 1 is 0, 0 minus log of A, or log A is negative, we can make it positive, the numerical quantity will become negative, so it is equal to minus 1.068 into 10 raised to the power minus 1. So this is, we can convert log A into A by taking anti-log. Okay, so value A can be written as anti-log of minus 0.1068, and therefore A is equal to 0.7814 microgram. This is our first answer. Okay, now come to the second part. We have to calculate in the same manner for 60 years also. So the amount left after 60 years. After 60 years. In the same manner, we will be using the equation, that is your the initial equation we have used here, that is K is equal to 2.303 divided by time taken log of A naught over A. We will rearrange the equation and then we put down the values, that is your 2.466 into 10 raised to the power minus 2. Here unit is per year. Okay, is equal to 2.303 divided by 60 years log of, we put down the values 1 A naught and divided by A. Okay, so we will have 2.466 into 10 raised to the power minus 2 per year multiplied by 60 years divided by 2.303 is equal to log 1 is the first one minus log of A. The numerical quantity that we have here after calculation, that is multiplication and division, we get it as 64.247 into 10 raised to the power minus 2. This is equal to minus log A, as log 1 will be 0. So log A is equal to minus 64.247 into 10 raised to the power minus 2. Therefore, A can be calculated as anti-log of minus 64.247 into 10 raised to the power minus 2. So basically value of A we will be getting as 0.2278 microgram. So this is our second value, that is after 60 year this is the amount left, and after 10 year this is the amount left. For calculating any sort of radioactivity related question, we have to remember that radioactive decay always follow first order kinetics. So we will be using our equations accordingly. Now come to the next question, 4.18. In this question, they are saying for our first order reaction, show that time required for 90% completion is twice the time required for completion of 90% of reaction. That is, time required for 99% completion is double of the time required for the 90% completion. So the information in this question is given what? First information, it is first order reaction. That is, it follow first order kinetics. Okay, and for first order kinetics, the equation that we use is time taken for a particular change is given as 2.303 divided by K log of initial amount divided by amount left at a particular time. Now we have to suppose here for putting the terms to make our calculation easier. So what we have to suppose that initial concentration, that is A naught, suppose it is taken as A, and the concentration at a given time is will be taken as A minus X, where what is X? X is the amount reacted or amount converted into product. Okay, so this is the amount left. Now we will put down the values in the first case. What is the first case? 99% completion. What is the meaning of 99% completion? 99% completion means that is amount which is reacted, that is X, it is 99% of A, that is the amount which we have initially. That is, whatever amount is there initially, 99% of it is converted into product. So since here we are writing here 99%, therefore it will be 99 by 100, therefore it is 0.99 A. This is the value of X. Okay, amount reacted. Now we will write down the equation for this. So time taken for 99% completion is given as 2.303 divided by K log of A divided by A minus X. A is amount present initially, A minus X, which is the amount left after some time. We can put down the value 2.303 divided by K log of A divided by A minus 0.99 A. So what we are getting here, we will be getting 2.303 divided by K, and we will get log of 100. We will simplify this part and this part, and after simplification we will be getting log 100. Okay, so what is the value of log 100? This is 2.303 divided by K, and log 100 is 2, so it is multiplied by 2. This is time taken for 99% completion. This is our first idea or the first equation that we will use. Now we will calculate time taken for 90% completion, which is equal to 2.303 divided by k. In the same manner, we will write down the equation. Log of initial amount is a and the amount at a particular time is a minus 0.90. Here we will write 90 because that is 90% completion a. Okay, so when we simplify the right hand side, we are getting 2.303 divided by k and log 10. Now log 10 is 1, so it is 2.303 divided by k into 1. Therefore, we are getting what? T 90% is 2.303 by k. Now we will find out the relationship between the two. We will first write down T 99% divided by T 90%. We will find out this ratio. T 99% we have calculated here. It is 2 into 2.303 divided by the whole quantity divided by k, and this whole quantity is divided by 2.303 divided by k. Now what we have, the terms which are common, we will cut down them. These will cancel out, okay, when we will simplify, and what we are left with, the T 99% divided by T 90% is equal to 2, or we can say T 99% is twice of T 90%, and this is what we have to calculate. That is, time taken for 99% completion is just double of time taken for 90% completion. This is the answer. Come to 4.19. Here they have given a first order reaction takes 40 minutes for 30% decomposition. Calculate T half. The very first information given in this reaction is again that it is first order reaction, and what they are saying in the how the reaction is taking place. For example, we have a specific reactant and it is decomposing into some product. So for this decomposition, it is taking 40 minutes, and decomposition is in what way? 30% decomposition. What is the meaning of 30% decomposition? Now come to the initial state. Initially, in the beginning of the reaction, suppose initial amount of your reactant is A, okay, and initially the product will be 0, okay, and amount left after some time will be A minus X if X amount of product is produced. Now here what is X? This X is 30% of initial amount of the reactant, which is A. So what we are getting here, 0.03 A. Okay, so we have here first for the calculation we have to calculate T half. So for the calculation of T half, first we require the rate constant. We do not know the value of rate constant, so we will calculate rate constant here. K is equal to 2.303 divided by T log of A divided by A minus X. This is equal to 2.303 divided by time taken as 40 minute log of A divided by A minus 30 by 100 A. Sorry, this value we have written wrong. This will come as 0.3 A. Okay, so this is 30 by 100 A. Now we will simplify the values, and what we are getting here, 2.303 divided by 40 minute. We are getting, after we will take a common here, and a will cancel out, and on after simplification we will be getting the value log of 100 divided by 70. Now this will be equal to 2.303 divided by 40 minute. Log of 100 by 70, we will be getting the value as 0.155, and after multiplication and division the answer will be 0.0089 per minute. This is the value of rate constant, because this value we will be utilizing to get our answer. Now for first order reaction, you know it very well that T half is equal to 0.693 divided by K. So here we know the value of K, so 0.693. This is the reason why we have calculated K, because we will utilize to calculate T half. So we are putting the value of K, which is 0.0089 per minute, and after division we'll be getting answer as 77.865 minute. This is T half. So this is your answer. Now come to the next question, that is 4.20. Now in this problem what they have given, for the decomposition of azoisopropane to hexane and nitrogen at 543 Kelvin, the following data are obtained. Okay, they have given a table. In the table they have given at different time interval the pressure in mm of Hg. Okay, first have a look here what we have. When a reaction has not started, that initially what we are having pressure only because of the azoisopropane. Okay, that is pure pressure of azoisopropane, and after at a particular time we will be getting a total pressure. It will be pressure of the reactant and as well as the product, because all the components are the gases. So we can write down for the same reaction the equation how the reaction will take place. So isopropane, you know, propane with 3 carbon atom, this is CH3, then we have azo group and double bond N, again we have CH3. This is azoisopropane. Okay, it will undergo decomposition, and what we are at 543 Kelvin, and what we are getting propane is CH3CH2CH3. This group is repeating 4 times because in hexane we are having 6 carbon atom plus nitrogen, that is N2 molecule. This is hexane and this is nitrogen gas. Okay, and here all the components are in the gaseous form, and that is reactants as well as product. Now have a look here. Initially when reaction has not started, initially that is at time equal to 0, we have only azoisopropane. So suppose that initial pressure of azoisopropane is taken as P0, and this at T second given in the table, this value is equal to 35 mm of Hg. Okay, and initially amount of hexane and nitrogen will be 0. Now after some time some amount of this has been converted into product, so amount left it will be initial amount minus amount converted, that is Px, and here Px amount of first and the second component will be produced. Okay, Now after some time we will be having all three gases in the medium. So after some time there will be a total pressure, okay, and this total pressure they have given P total at a given time. This total pressure will be the sum of the pressure of all three gases, that is P naught minus Px for azoisopropane plus Px for hexane and plus Px for nitrogen. So when we calculate this, we will be getting value P naught plus Px. So from here we will be getting the value, we can calculate the value of Px. Px is can be written as P total minus P naught. Okay, this thing we have to remember in our mind. The data which is given to us in the table, in this data they have given us to P naught, that is initial pressure in case of pure azoisopropane, or they have given the total pressure which is the mixture of all three, but we do not know individual pressure of the product or the partial pressure of reactant after some time. Therefore whatever calculations we can do calculation only in terms of these quantities. So therefore we are doing all these simplifications. So now we substitute this value of Px. How to substitute? Have a look here. This P naught, what is P naught? It is synonymous to the initial amount of the substance that usually we take as A, and the amount left at a particular time is taken as A minus X. Yes, so this A minus X is basically P naught minus Px. So P naught minus Px, we cannot write Px because we do not know the value of Px. Okay, therefore we will convert it in terms of those pressures which are known to us. Therefore A minus X, which is synonymous to P naught minus Px. Okay, this P naught minus Px can be written as, we will put down the value of Px here from this equation. So it is P naught minus P total minus P naught. Okay, so we will be getting here P naught minus P total plus P naught, which is equal to 2P naught minus P total. Okay, this is the value which we are going to use, that is P naught minus Px is equal to 2P naught P total. And why we have done this conversion? Because we know what is P naught, we know what is P total from the table. Therefore we can find out A minus X easily in any case if we know the initial pressure and the final total pressure. Okay, now come to the problem that what we are going to calculate. We have to calculate the rate constant. Okay, so we'll write down the equation for the rate constant. Rate constant, that is K, is equal to 2.303 divided by time taken for a particular change log of initial amount, that is A, divided by A minus X. This is the equation in terms of the amount or the concentration. Now we will write down the same equation in terms of the pressures which are provided to us in this table, from this table. So we will write it as A is nothing but initial amount of the substance, which is P naught. So it is 2.303 divided by T. This is equal to log of P naught, initial amount, divided by P naught minus Px, which is A minus X. This is what? 2P naught minus P total. So we write it here 2P naught minus P total. Okay, we have to use this equation for the calculation in all cases. sorry, this is not into. So 2.303 divided by T log of P naught divided by 2P naught minus P total. We have written the equation in terms of the known parameter, which is initial pressure P naught here, and the total pressure at a given time, which is P total. So put down the values one by one. We have two observations, so we will do for the first case, that is at T is equal to, the first value of time is 360, T is equal to 360. So we will calculate a value of K. K is equal to 2.303 divided by time is 360, as we have chosen. Log of P naught is 35. It is given in your table. P naught is 35 and P total is what we have in first case 54, in second case 63. So we are doing the first case. So we are going to use 54 divided by 2 P naught. 2 P naught is what? 35 into 2 will be 70. So 70 minus 54. Okay. So this is equal to 2.303 divided by 360 log of 35 divided by 16. Now we will calculate the value, and after calculation finding out the log of the values, because we have log 35 and log 16. So it is 2.303 divided by 360 into 1.544 minus 1.204, and we are getting value as 2.175 into 10 raised to the power minus 3 per second. Okay, this is the value of K in from the first observation. Okay, so similarly at T is equal to 720. We will write the equation in the same manner. K is equal to 2.303 divided by 720. The value which is given here 720, and for this pressure, total pressure is 63. Okay, so 720 second log of, we will write down 35 divided by, 35 is P naught, it will remain same, and 2 P naught will also remain same, that is 70 minus second value P total is 63 in this case, so we will write down 63. After calculation and simplification, we will be getting value from here as K is equal to 2.235 into 10 raised to the power minus 3 per second. So this is the second value. This is the first value, and here is the second value. Fine. So therefore we have to take average of the two. So therefore K average is equal to your K1 and K2. K1 is this one, the calculated in terms of the first, and K2 is this one. This is K1 plus K2 divided by 2. So it will be the first value, that is 2.175 plus 2.235 into 10 raised to the power minus 3 per second divided by 2. So value will be that we are getting here is 2.20 into 10 raised to the power minus 3 per second. This is the value of rate constant, and this is our answer. Okay, this is all for today.